We're now going to be looking at series summation techniques. So the different ways in which we can find a general term, a general expression for the sum of a series. Now what we mean by a general expression is that it'll be an expression in n, where n stands for the number of terms, so that if we wanted then to find out the sum to a particular number of terms, all you could do is just put in a value for n, and it would give you a numerical sum, a numerical value for that series up to that number of terms. Now the first type we're going to be looking at is where the rth term can be expressed as a polynomial in R of degree less than 4. Now if you remember, a polynomial is an algebraic expression where the power that the variable is raised to has to be positive, and it has to be an integer, a whole number. Now for this type we're looking at those where the degree is the highest power in a polynomial is less than 4, so its highest power would be 3. So we've got an example here where we need to sum this series to n terms. So we have 3 factors there, 1 times 2 times 4 in the first term, then the second term is the result of multiplying 2 times 3 times 5, and the third from 3 times 4 times 6. Now we might ask ourselves, how do we know that this particular series fits this type? Well, sometimes we're given the series as just as a series like this, where you just see a few terms but you haven't got the rth term, or sometimes the rth term is given to you. Well, in this case we need to actually find the rth term. We need to look at the pattern that's involved, and we need to find the relationship between these factors, between the terms, and think, okay, what is the rth term? So we by looking at that, we know that the first factor in the first term of the series is 1, and that the value of that factor increases by 1 for each successive term. So the first factor in each term, it starts at 1, then it's 2, and then it's 3. And so that means that we can use the variable r for the first factor, and the coefficient of r, because that is increasing by 1 each time, the coefficient of r is going to be 1. When we look at the second term, it begins at 2, but also increases by 1 each time. So we're going to use r and the coefficient of r being 1, but instead of just r, because it starts at 2, we have to go r plus 1, because for the first term r equals 1. So then how do we get 2? Well, we need to add 1. 1 plus 1 equals 2. So let's just start writing this down and we'll see. So if we just let Sn represent the sum to n terms, and we're going to use sigma notation. So we're starting at r equals 1 and summing to n terms. The first factor, we're going to use r. The second factor is r plus 1. Now the third factor, it also increases by 1 each time, and so again the coefficient of r is going to be 1, but because we're starting at 4 for the first term, we need to write r plus 3. Okay, so in terms of just writing the rth term as a factored expression, then it's r times r plus 1 times r plus 3. Now what we're going to do is we're going to expand those brackets so that we have r, we keep the r out front, and we'll just expand the second two factors. So we have r squared, and it'll be plus 4r plus 3. And we'll continue with that. So that it becomes r cubed plus 4r squared plus 3r. Okay, so that's our expression that we're summing. Alright, now we're going to use our understanding of the properties of sigma notation so that we can split this up into 3 separate series with sigma notation. So we can write sum from r equals 1 to n terms of r cubed plus the sum from r equals 1 to 4r squared and similar for the last one for 3r. Okay, so we've split it into 3 separate series, and remember we've got a constant here times the function, so we can put this 4 out the front and we can put the 3 out the front. Okay, now you'll notice that each of these 3 series are those special series we looked at previously. So we can write the general expressions for each of those now that we've got it in this form. Okay, and that's what we'll do here. So you can see that I've written those there. Now these are all the ones that are on your information sheet. The only thing that you need to notice is that because it's 4 times and 3 times, we need to have those there. Then we could look at, we could possibly cancel here, but it's not really necessary because what we're going to do is going to combine these into a single fraction. So we need to look for a common denominator. Okay, so we can see that the common denominator, the lowest common denominator is going to be 12. So we'd need to multiply this by 3 over 3, this by 2 over 2, and this by 6 over 6. Okay, so that's what we'll do, and I'll put that down now. So here is that next line, and you can see that I've done just that to get the single fraction there over 12. Then I will look at, I will take out a common factor of n plus 1 and n, and then we'll simplify it from there. So I'll scroll down. Scroll down and continue, and I'll just put all the rest of that on there, but it's also in your notes for this particular example. So you can see that I've taken that common factor of n times n plus 1 out, and the remaining is inside the square brackets. So then the next step is to expand and collect any like terms, and then factorize that last expression in those square brackets as far as possible. Okay, so it's simplified. We expanded and collected like terms to get the 3n squared plus 19n plus 26, and then that factorised to n plus 2 times 3n plus 13. And so that last line there is our required result, because the question asked us to have it in factored form. Now it's really important that your algebra skills are excellent, okay, and your ability to factorise is really, really good. Having said that though, when it comes to the exam, you need to be working as fast and efficiently as you possibly can. Okay, so when you get to that expression 3n squared plus 19n plus 26, okay, put it in your calculator to factorise that. Okay, you need to be able to save time where you can. So certainly at that point there, just put in your calculator, because the next step is fine. You can't really show any further working. No further working is necessary to go between that second last and last line. Okay, so that's our result. So what we can do then, we could find the sum to 50 terms if we wanted. Just to put n equals 50 and evaluate the expression, and that would give us the sum for that series that was given at the start, the sum to 50 terms. Okay, so we're going to give, I'll do another example in the next video lesson.